This video is about bypass capacitors. It corresponds to section 11.10 of the Applied Analog Electronics textbook. Bypass capacitors are sometimes also called decoupling capacitors, and that seems to be favored in some of the more modern textbooks, but I prefer the older term bypass capacitors, and it is still in pretty common use. Okay, what are they? In a lot of circuits, if you look at the schematics or try to reverse engineer what's going on in the schematics, you'll see a whole bunch of capacitors that don't seem to be doing anything. You've got, like 5-volt power supply or something, and you've just got a capacitor from there to ground. I mean, if you think about it, you've got a DC voltage across the capacitor will charge up to that DC voltage, and then that's it. You're done. Nothing happens. So what's the point of these capacitors? Well, the point is that the schematic is a simplification of the real world, as all things are in what we do in engineering. Everything's a simplification. The wiring that goes from the 5-volt power supply to the capacitor and to other parts of the circuit is not a perfect node. That is to say, not every point on that wiring has exactly the same voltage. And we simplify it to being a node because it's a lot easier to think about, but there's sometimes when we have to worry about things like the resistance of the wiring. So if we've got something where we've got our 5-volt power supply, and then we've got wiring that's got a little bit of resistance in it, and we're looking at this at various points to drive various parts of the circuitry, well, if the current through here fluctuates, well then the voltage drop across the resistors is going to fluctuate. And instead of having a constant voltage here, you're going to have a fluctuating voltage. And the fluctuating voltage may not even be the same in the different places you're looking at the wire. So instead of the 5-volt thing really being a node, you may have to think about it as a bunch of resistance. And if you're working on some high-speed stuff, you may even have to be worrying about the inductance of the wiring. And this means that the modeling gets much more complicated if you have to really worry about that. So what a lot of people are trying to do, however, is to make the 5-volt, or whatever your power supply is, look like it's constant. So that as far as your circuitry is concerned, it can treat it as a constant voltage. And so what is often done is to put a capacitor here where you're actually trying to look at the voltage. And this does two things. One is that when you've got this fluctuating voltage here, well, the capacitance passes through some of the fluctuations to ground, shorts it out, at least if it's a high enough frequency signal. This is a very low impedance here, and so the signal gets attenuated. The DC doesn't change, but the higher frequency stuff gets reduced substantially. You've got essentially a low-pass filter. So you reduce the noise coming in. Another thing is that if the fluctuating current is coming from one of these chips, so this is where you've got that fluctuating current, well, that fluctuating current can come from charging and discharging the capacitor rather than coming from the power supply, and so you're reducing the amount of noise you're injecting into the power supply node. So the bypass capacitors do two things. They protect the chip from fluctuations in the power supply, and they protect the power supply wiring, which is to say the other chips, from fluctuations in current that this chip takes. So it both, it's like wearing a mask for the COVID. It's not only protects right where it is, but it protects everyone around it. Okay, what size capacitor do we use for this? Well, if we're trying to get good reduction in noise, we're going to say, well, we've got a small resistance here. If we're trying to reduce the noise, maybe we need a large capacitance in order to get reduction and, get a low-pass filter with a low corner frequency. And so you want to use big capacitors. The trouble is, big capacitors are expensive. They're also big physically. And so you can't say, well, I'm going to put a capacitor that's this big on top of each little chip that's, tiny little thing. So you want the capacitors to be smaller than the chips that they're protecting physically, and you want them to be cheap because you're putting them everywhere. So you want cheap capacitors, and you want physically small capacitors. How do you get all those things at once? Well, you don't. But the usual trade-off is to use the high dielectric capacitance ceramics. So I looked on DigiKey to see what were the most popular capacitors, and the most popular capacitors were the X5R and X7R capacitors. Those are high dielectric constant, but not the really cheap ones that vary enormously with temperature, but decent sort of dielectric, but very high dielectric constant, so that you can get a physically small capacitor, which is not all that big a capacitance, but big relative to the size. And they're cheap. So a lot of bypass capacitors are like this, and the size that was most popular on DigiKey was 0.1 microfarad. And it's probably just a popular size because it's point at which these capacitors start getting more expensive. If you go to bigger ones than that, they start costing a lot more. And you don't gain a lot by going just a little bit bigger. These are good enough for most digital work where you're working with very high frequencies, but they're the ones you put right next to the chips. I've been using for my own work usually more like a 4.7 microfarad capacitor. That's because I'm usually not working with the tiny little chip capacitors that are surface mount components, but are the little bit bigger disk capacitors like we use in class with the breadboards. And the 4.7 microfarad ones are still reasonably cheap there. You pay a lot more for just getting the thing as something you can plug into a breadboard already, and so the extra cost for the 4.7 microfarad rather than the 0.1 microfarad is pretty small. I'm not doing millions of them anyway. I'm only doing tens of them usually. So my popular size is 4.7 microfarad, but anything in the range 0.1 microfarad to 10 microfarads you'll see sometimes as a bypass capacitor. Now there are a couple other times where you'll see bypass capacitors, and that is if you've got a power supply that's having to drive a pretty noisy source, like we'll be actually seeing in the power amplifier that we do next quarter. The power amplifier injects a lot of noise into its power supply. Then you might want to do a capacitor that's like 470 microfarads. Now 470 microfarads you're not going to get in these cheap ceramic capacitors. They just don't make them that big. Instead, you're going to want to get an electrolytic capacitor. And the electrolytic capacitors easily come in these bigger sizes. They have some limitations on them. They have to be they're usually polarized, which means you have to make sure that the plus end is connected to the more positive voltage, because if you hook them up backwards, you can blow them up. And you don't usually want to do that. I mean, I have seen people do it deliberately just to see them blow up, but usually you want to put the capacitors in the right way around. The electrolytic capacitors have a fairly large equivalent series resistance, so you really need to model them as a resistor in series with a capacitor. And that means that they don't do such a good job of removing high frequency noise, because you've got high frequency noise here. Well, the resistance here is substantial enough that you don't get the reduction you might want to see or might want to expect from just this big a capacitor. So quite often when you've got a big capacitor like that, you will often see a small capacitor put in parallel with it, and this one might be 1 microfarad or even the 0.1 microfarad. And this capacitor is one that doesn't have such a large series resistance, and so it can take care of the higher frequency stuff that this thing still has too much too much impedance really to do much about. All right, what else do you need to know? There is one other place we use something that looks a lot like a bypass capacitor. It's a little bit different. It's still on a constant voltage, but that is when we do our voltage references where we're trying to say, hey, I've got my 3.3 volt maybe power supply here, and I want to get 1.65 volts here, and maybe I'm putting that distributing that around my system, or I might be putting it into an amplifier or something. I want this thing to be constant voltage. I really do want this to be 1.65 volts. I don't want it to be taking any noise from the power supply. If there's a little bit of noise on the power supply, I don't want it appearing here. My voltage reference, I want it to be very fixed. So I might put a large capacitor here, acting, again, we've got essentially a resistor that's the Thevenin equivalent to 1.65 volts, and then a capacitor here. And this capacitor, I generally make this sort of as big as I can comfortably afford. So I'll often put a 10 microfarad or my favorite 4.7 microfarad there to try and filter out any power supply noise from my reference voltage. And this is, you can think of this as a bypass capacitor if you want. Notice that putting it here has much more effect than putting a capacitor just directly on the power supply, because I can make these resistors pretty big. I mean, these might be 220 k ohm resistors if I don't have to take any current. And then I've got a very large time constant for this thing, whereas this capacitor here has got only few milliohms or tens of milliohms of wiring resistance, and so even with a huge capacitor here, I'm not going to be seeing the same sort of low frequency filtering that I can get with a big capacitor and big resistors. And so if I'm trying to get rid of 60 hertz hum or something like that from my reference voltage, bypass capacitor on the power supply is not going to do it for me. That'll get rid of very high frequency stuff, but it's not going to get rid of the low frequency stuff. To get rid of the low frequency noise as well, then I need to have big resistors. And notice I can't take current from this thing because there's almost no current available. If I take any current, the voltage will drop. So that's got to be something where I need the voltage, but I don't need to take current from it. All right, that's probably enough about bypass capacitors for now.